Hey everyone, so we're going to be talking about our next biomolecule, which is going to be lipids, which form the structural components for cellular membranes. So lipids pack about 2 times the caloric content of carbohydrates, so a big source of energy. We can hydrolyze carbohydrates to use in other metabolic pathways or anabolize them in certain metabolic pathways to use them for immediate energy. Lipids usually are used for energy storage. So it's for storage, or sorry, carbohydrates are used for the immediate energy, and lipids are used for the storage of energy. Lipids are also used as the main component for the cellular membrane of many cells that are in our body, so not necessarily stored in our body. There's also a lot of vitamins that are fat soluble that need to be transported around, and lipids are able to do that because of their unique duality of properties that they have on them. And so lipids aren't necessarily classified by a single function group. Um, They're instead classified by the physical property of solubility, usually. So they're not classified by functional groups and instead are classified by solubility. So we have things that have soluble and then insoluble lipids. So steroids are going to be insoluble, and everything else here are generally soluble. And when we say soluble, we mean solubility in water. And it doesn't necessarily mean that the lipid individually will be completely soluble, but we can form certain things like emulsions, micelles, that can then be solubilized in water with lipids. So those can include fatty acids, and the fatty acids are long chain carbohydrates, um, comprise triglycerides, phosphoglycerides, waxes, and sphingolipids, which then can be divided into glycolipids, which can be antigens that present on the surface of the cell, combining carbohydrates, and also sphingomyelins as well, which can be the structural component for a lot of membranes, along with phosphoglycerides and phospholipids. And so we can also classify them by the saponifiability. So saponification, if you guys remember, is base catalyzed hydrolysis, where when we catalyze an ester bond, for example, it'll leave us with a carboxylate ion instead of a carboxylic acid and an alcohol, right? So this is the hydrolysis, and we need a water molecule to make up the two um, OH and the two hydrogens that we pick up there. And so this is classified whether or not they go through hydrolysis. And so we have saponifiable lipids, which follow the same trend as the solubility trends, and non-saponifiable, which include the prostaglandins and the steroids. We have simple and complex lipids for saponifiable lipids, which will simple lipids will constitute waxes and oils and fats and triglycerides as well. So these are going to be things that only contain alcohols, carboxylic acids, and esters. Complex lipids like phosphoglycerides and sphingolipids will have other more complicated functional groups, which is why they are broken up into those categories. And so simple lipids, again, are only comprised of carboxylic acid, of fatty acids, and alcohols, right? So if we have a simple lipid, for example, this is going to be a example of a wax here. It's an ester, which if we were to hydrolyze that, we would get a long chain alcohol and a carboxylic acid. So I'm just drawing the squiggly lines here just to represent the R groups. I don't feel like drawing all of them out. Complex lipids may have other more complicated components. So if we have a sphingosine backbone, for example, this can then form an amide bond with a fatty acid, which will then also form a phosphoester with perhaps an amino alcohol. So a positive charge there, minus charge there, for example. This we see we have a much longer are a much more complicated set of functional groups here. We have a phosphate group, we have an amino group, an alcohol, ester, an amide, and a long hydrophobic chains. So these would constitute what would we call complex lipids, right? So the simple lipids are alcohols and fatty acids. The complex lipids are going to have other more complicated components to them. So fatty acids are going to be carboxylic acids that have that form the structural components of fats, oils, and lipids. They usually have an even number of carbons ranging from 12 to 22, and they're classified by the number of double bonds, right? It's the same way in organic chemistry we talk about saturation. Saturated fatty acids are only single carbon-carbon bonds, and unsaturated fatty acids will have a carbon-carbon double bond, at least one. We only need one of those to be classified as an unsaturated fatty acid. And that's because we're basically taking two spots of hydrogen. When we hydrogenate a double bond, we place a double bond with two hydrogens, right? So it has to do with the number of hydrogens that are on the molecule. And so fatty acids have a carboxylic acid side and an alcohol side. And at low pH, so potentially in saponification, we'll have a carboxylate ion. At high pH, they will have a protonated carboxylic acid group. And sorry, this isn't a carboxylic acid side and a alcohol side. These are actually going to be a polar side and a non-polar side. And so this would be both of the polar sides for both of these. The charged is more polar, and then the long chain saturated or unsaturated side, these are going to be the non-polar parts, and regardless of whatever the pH of the solution is. And so the degree of the saturation of the fatty acid affects its shape and physical properties, right? So if we have an example, a saturated fatty acid, we see that this looks like a linear structure. But let's say we add a double bond, so we can make it an unsaturated fatty acid. And if it is perhaps a cis double bond, this introduces a kink into the structure. So this is now a bent structure, right? So the physical shape has been altered because this is a planar bond that restricts the three-dimensional space of the fatty acid and the lipid, right? So the degree of saturation affects that. And so this, therefore, then affects the melting point of fatty acids, right? So if we look at using the same colors we did before, we have the polar head and we have the nonpolar tail. If we have a unsaturated fatty acid, all these bonds can rotate and move around freely, so they're more likely to overall, if this was an electron density map, look at having a relatively linear conformation. And so what this means is that if we had a bunch of these next to each other, they would all most likely be able to align to maximize the intermolecular forces. And these are all mostly going to be London dispersion forces because the nonpolar side is probably going to dominate the forces. So these are London dispersion forces, right? So London dispersion forces scale with molecular size. So these order neatly. If we have an unsaturated fatty acid, we still have the polar head. And we still have carbons and hydrogen, so we have a nonpolar tail. But let's say now we have a kink in the structure, right? So this is the non-polar tail. Now we have a kink in the structure. And so this kink, can then restrict the way that these lipids can then orient themselves. So let's say this one goes down, and this one. So maybe we have a lower density of the fatty acids here. So we get less maximization because it's really just these parts over here, less potential contact for London dispersion forces, right? And so this means that the intermolecular forces are weaker for this. So intermolecular forces are weaker. And for saturated fatty acids means intermolecular forces are stronger. And this means that the melting point is going to be lower for unsaturated fatty acids. So this is going to have a lower melting point, and this will have a higher melting point because of this. And so because of the three-dimensional shape of the saturated versus unsaturated fatty acids, we get a change in the physical properties of these. And so mostly unsaturated fatty acids will be liquids at room temperature, where saturated fatty acids are going to be solid. And when we talk about triglycerides and waxes and versus oils and fats, that's kind of how we distinguish them. Is what state of matter are they in? And so if we were to look at these different fatty acids here, we say what, and we just had to guess on what, not guess, but make an educated guess on the different states of matter. We could say, well, this structure up here, the top structure, is going to be the most nonlinear, means it'll have the lowest melting point. The down here will be the, if we rank it in terms of melting point, so rank in terms of melting point, this would be the lowest melting point. This would be the second lowest melting point because they're both unsaturated, but this one is more distorted at the top. And then the ones in between, we say, okay, well, they're both unsaturated, or they're both saturated fatty acids, but one has a longer carbon chain, which means that it'll have stronger intermolecular forces. So then this will be the second lowest, or the second highest melting point, and then this one will be the strongest melting point. And so based off of this, if let's say this was a solid, then I could say this would definitely be a solid, and then these two would most likely be liquids at room temperature because of this. This is just making an educated guess based off of the structure of these fatty acids and their degree of saturation. Fatty acids can also form what are called micelles in aqueous solutions, so in solutions of water. And so they can form a micelle in oil or in water. And what that looks like is we have the the polar heads are going to surround and encircle each other, and the polar tail or the nonpolar tails are all going to stay close to each other and face inward to form a three-dimensional sphere called a micelle. And so this is the same chemistry principle you guys have been learning for a couple of years now, that like likes like. So the nonpolar stuff, if we're in an aqueous solution, means we have a bunch of water floating around here. The polar head likes the water, and the nonpolar tail likes other nonpolar tails. And so to maximize this interaction, the fatty acids will orient themselves in high enough concentration solutions. So this is at high concentration. At low concentration, instead of forming micelles, what will happen is if we have an aqueous solution and then it has an air interface like this, is the polar heads will orient themselves on the top layer of the solution, and the nonpolar tails are going to orient themselves up to then stay away from the water, because the air is technically going to be less polar than the water molecules. So this will be air like that. So we can form micelles in aqueous solutions or monolayers, right? So this is called a monolayer, and this is in low concentration that we form these monolayers. So then we have fats and oils, and these are going to be our most abundant lipid in nature. And so they are called triglycerides. because they are an ester that's formed from a alcohol, a trihydroxy alcohol, glycerol, which looks something like this. This is a simplified drawing of what it looks like. Each edge and intersection here represents a carbon atom and a fatty acid, right? So we have our fatty acid, and these will come together to form a triglyceride. We get an ester linkage at each of the alcohols, like that, and this is our triglyceride. And so natural triglycerides generally have different fatty acids at each of these positions. So this would be like fatty acid 1, 2, and 3, because if you have a bunch of fatty acids that are in solution, you're generally not going to have one preference to making a triglyceride with one over the other. So you usually have different fatty acids at these positions. In the lab, you can have a single fatty acid at all these positions because you can control what fatty acids are in the environment. And so solid triglycerides, sorry, these are not triglycerols, at room temperature are called fats, and then liquids at room temperature are called oils, right? So those are the difference between fats and oils. They're all triglycerides, which are um, ester bonds formed between fatty acids, and glycerol, which is a trihydroxy alcohol. And so we can have a simple diagram for these, and we'll have these for a lot of lipids. To simplify them, we have a glycerol that then has three fatty acids that are bonded to it. And so when we don't feel like drawing these long, because these fatty acids can have up to 22 carbons each, these long structures, we can draw this, and this is called the block diagram for triglycerides. And so I have a couple examples here. I encourage you guys to go through on your own and attempt these examples. So here we have a triglyceride that forms between glycerol and the three molecules of myristic acid, which is a saturated fatty acid we have here. And so you're just making an ester bond. You can draw it in the kind of nice, neat, oriented structure we have here, but this can also make a more interesting three-dimensional structure as well. We can also do this with a mixture of different fatty acids. And so we can form at least 9 different fatty acids based off of these three fatty acids. If they're in solution, you can have all of the same one, all different, mix and matching one or two at the different spots on the triglyceride. Right, so this is just giving you practice on drawing the different triglycerides. We can have different reactions of fats and oils, and so we can use an acid to cleave esters. We can perform a hydrolysis reaction. And so if we have our triglyceride of our different fatty acids, we need water for each. So we need 3 water molecules, and then it can be acid catalyzed, which means that we'll have the protonated form of the fatty acid when we hydrolyze this ester bond, which we've done plenty of times before in this class. 3 water molecules because we need 6 total hydrogens and 3 oxygens to then make the carboxylic acid and alcohol groups. And what we'll get when we do this is we get 1 glycerol molecule and 3 different fatty acids. And so when we want to break down lipids into smaller metabolites, if we're making triglycerides, for example, we go through a hydrolysis reaction. We can also use a base to do this, which will be a saponification reaction. And this is going to be almost completely identical to this reaction that I have just drawn, except instead of having a protonated fatty acid, we're going to have a deprotonated fatty acid because we're in basic conditions, right? So we're not going to have H plus there. We'll have OH minus, we will have deprotonated fatty acids. And so we can also go from unsaturated fats and oils to saturated fats and oils. And so this is a reaction you guys have seen before too, not in this class, but in your previous organic chemistry class. We can have a hydrogenation reaction, which is a mildly reducing reaction. And that hydrogenation reaction, so let's say we have an alkene like this, we have hydrogen gas in the presence of a platinum catalyst. This will get rid of the double bond, and in its place, it'll put two new hydrogens, right? So saturated fatty acids were one where there's no double bonds, only hydrogens in place. And so we can do a hydrogenation reaction of fats and oils to then make them saturated fatty acids, right? And so this can make it a liquid into a solid by doing this because we're maximizing the intermolecular forces now. And so here's some more practice for you guys. You can draw the hydrolysis. This is a more realistic 3D representation of the fatty acid, right? Because the glycerol molecule can rotate. These are all single bonds. They can rotate and move around with respect to each other. So that is a glycerol in the middle, and the fatty acids will all go in different directions. So you can do this for hydrolysis, saponification, and hydrogenation. Next, we'll talk about our next simple lipid. Right, so this is also a simple lipid, except this is going to have the ester functional group to hold together. Instead of a glycerol molecule and three fatty acids, we can combine a long chain alcohol with a fatty acid. So we have something like this. This gets added with a long chain alcohol, so this is probably something also insoluble to then make an ester bond that looks something like that. And see, these are very nonpolar molecules, and so this actually makes hydrolysis or makes them insoluble in water. So waxes tend to be very insoluble. If you've ever used like hair wax or anything like that, it's pretty hard to just wash off with water. And this makes hydrolysis very difficult. And so you might ask, well, why does it make hydrolysis difficult? Well, if you're insoluble in water, we need H2O to hydrolyze an ester bond. And so if we don't have water around, it's hard to hydrolyze that ester bond. So if we don't have water around, it's hard to hydrolyze the ester bond. So that's why it's difficult to hydrolyze waxes in water. The next lipid we have is a complex lipid. This is our first complex lipid. So these are generally referred to as phospholipids. And they're similar to triglycerides, except we have other functional groups besides the usual ester, carboxylic acid, or OH functional groups. And so, like a triglyceride, we have two fatty acids, except one of the spots is taken by a phosphate that is bonded to an amino alcohol. Right, so if we had the block diagram, we still have our glycerol. We have two fatty acids. And then now we have a phosphate that's bonded to an amino alcohol. And I'll go over this block diagram again. And so what this amino alcohol tends to look like, we get different amino alcohols depending on the type of membrane usually that we're looking at, is it's going to have a positive charge, amine group, and an OH. The phosphate group is going to be negatively charged and then connected via ester bond, so it creates a phospho bond with the glycerol that we have, right? So we get a negative and a positive charge on this side of the molecule. This makes this side of the molecule very polar. And so that's why this forms membranes very well, because we have a very, very polar side of the molecule because of full charges there. So again, the block diagram for this looks something like this. We have the glycerol. We have the phosphate group that's bonded to the amino alcohol, and then we have two other fatty acids, which is almost identical to a triglyceride, except the last row here is taken by phosphate and an amino alcohol. And this makes them very, very polar, and so they're very good for making membranes. And so the concentrations on of charges on the phosphate, spell this a little better, the phosphate plus the amino alcohol make it extremely polar, like I just said, while the rest of the molecule remains nonpolar, right? So we're going to have two nonpolar tails that are associated with the fatty acids that are there. And this allows them to function as the structural component for a cellular membrane because the polar heads, the polar side of the molecules, are going to stay away from the nonpolar parts. And so here we have two potentially phospholipids, and on either side we have water, which will be attracted to the polar heads, and then the nonpolar tails will stay together. So the same way we had the micelle creation with phospholipids, we can do that, except we form a bilayer, right? So this is a lipid bilayer. So we have two phospholipids here, potentially phospholipids. And so the common amino alcohols that make up the phospholipids are lecithin, cephalins, and cephalins. And so just depending on the different type of body or different type of area you find them in the body, you'll find the different amino alcohols there. We're not going to worry about that too much right now. We're more focused on just the structure of the phospholipids in general. And so if we had to label each of the parts here, we see that this would be the phosphate. This is our amino alcohol. These are our two fatty acids. And this is our glycerol. And so we can also draw a typical structure for a cellophane containing the cation of ethanolamine. So I will let you guys try and do that. And so you can draw a structure similar to this one, maybe ignoring all the CHs, and instead draw the carbon skeleton for that. The next class of complex lipids that we have are sphingolipids. And so these do not have a glycerol and they have one last fatty acid, but they instead have a sphingosine, right? So this is a sphingosine molecule. And this is a long chain unsaturated amino alcohol, unsaturated because it has this double bond right there. And the difference between this and glycerol is also the fatty acid is connected via an amide linkage instead of an ester, right? So the amide is going to be created here. So this is where we'll have our fatty acid binding to this point. This will be I'm not going to draw this permanently, but this would be the long chain amino alcohol that kind of replaces the role of the other fatty acid. And then at this position here, we're going to have our phosphate and our amino alcohol. So they're very similar to phospholipids. So this is taken by an amino alcohol. So the amino alcohol and phosphate, O minus, NH3, for example, go right there. So this is how the sphingolipid kind of behaves. And this also allows it to function as a membrane. And so generally the block diagram for what the sphingolipids look like is we take the place of one of the fatty acids with the sphingosine backbone. We have one fatty acid that's connected via an amide linkage. We don't have to indicate that here. This is a fatty acid. And then we're going to have our phosphate that's then connected to our amino alcohol, right? So we see that all of this long chain amino alcohol, long chain fatty acid is going to be nonpolar, and this is going to be very polar. And so these, again, are going to be structural components for membranes as well. And they just depends on what part of the body you're in. Here's an example you guys can look at and see if you can identify all the different components of the following sphingolipid. And so this is sphingomyelin, a specific sphingolipid. And so our next complex lipid is going to be glycolipids, and like glyco suggests, these are going to have a carbohydrate instead of the phosphate group and amino alcohol. And so these are bound to the anomeric carbon when we talked about carbohydrates in the ring structure. So if we have a carbohydrate like this will be bound to the sphingosine, right? So the sphingosine backbone, I'm just going to draw a block structure here, the sphingosine. And then this also has its fatty acid component as well. And so this right here was our carbohydrate. Our Hayward projection of a carbohydrate. And so these are bound on the anomeric carbon, right? So the anomeric carbon again is the carbon that is first in the chain. It's originally where the carbonyl group was in the linear structure of the carbohydrate. And so these can be presented as antigens on the surface of red blood cells, for example. And this carbohydrate, if we think about this is going to be a very polar group. And this side of the molecule is going to be very nonpolar. And so the nonpolar side anchors itself in the cellular membrane, and then the carbohydrate can be expressed on the surface and wants to surround itself with the polar water molecules that exist in the body. Right, so these antigens allow the cell to communicate via molecular interactions. Right, so you have an antigen receptor. This allows for communication between the different parts of between the cells in different parts of the body. Right, and so on red blood cells, for example, if we had a red blood cell, your blood type can be given by the different antigens that you have. And so if you had a bunch of B antigens on the surface of your red blood cell, the sphingosine and the fatty acid are going to be anchored in the cellular membrane of the red blood cell. And if these were B antigens, that would give you a B blood type. If you have mixed blood types, it means you have a combination of both of them, right? So if you have O and B, then A and B, you can have AB blood type, right? So these are the antigens that present themselves on the surface of the cell. And so you guys can draw a typical glycolipid for the following glucose molecule. You can know which is the anomeric carbon. You guys should be able to identify which the anomeric carbon just by looking at the structure and seeing where the extra CH2OH group is, right? So glucose, and it's the only one that doesn't have a stereocenter here, right? The last lipid that we're going to talk about are steroids and hormones. And so these are non-saponifiable and insoluble lipids. So these are insoluble in water. And so they're distinguished by a four-member polycyclic structure. So polycyclic structure. And what this structure looks like, it'll be modified depending on the specific steroid or hormone. Let me draw this a little lower, by the specific hormone or steroid that you're looking at. But they will all have this typical four-member ring structure. So we have three 6-member rings and one 5-member ring. And you can modify this with double bonds, different substituent groups all over this ring structure. And the most abundant steroid or hormone in the body is cholesterol. And so if you're ever trying to remember if this is a complex or a simple lipid or a saponifiable or non-saponifiable, you get buildup of cholesterol in your body because the cholesterol is actually not soluble in the water. So that's why it can build up in your arteries and stuff. And so that's why buildup of these things is not favorable. And so these will generally embed themselves within the cellular membrane. And so this is what's called a fluid mosaic model to describe different location of lipids. This isn't a perfectly drawn steroid or hormone, but the steroid or hormones are nonpolar, so they're going to be inside the membranes. hormones. Here we have our glycolipid, right? Those are the carbohydrates presenting themselves on the surface of the cell. And then these would be the phospholipids or the sphingolipids, which form the structural components of the cellular membrane. So this is a picture here. This would also potentially be a transport protein that we didn't talk about because it's not a lipid, but this would be a transport protein that then allows things to move across the membrane. But the lipid component of the membrane is organized in this way generally. So this is called a fluid mosaic model because things are allowed to move freely. We don't have tools that kind of organize things in our cells. Things are just moving around based off of intermolecular forces and where they like to be based off of their physical properties. So again, the sphingolipids and phospholipids form the lipid bilayer because of their unique polarity. Then we have the steroids, which are insoluble, so they find themselves inside the bilayer away from the aqueous solution of the water that's on both sides of the cells. And then the glycolipids, they communicate or help communicate with other parts and other cells, whichever cells those may be. They could be part of the immune system, or they could be other red blood cells that they're communicating between. And those have the nonpolar side that anchors itself in the membrane. And then they have the carbohydrates, which are polar, that can then express themselves on the surface. And so the lipid membrane is generally have unsaturated fatty acids to allow for more flexibility. Remember, the saturated fatty acids could pack tightly, and if you have unsaturated fatty acids, this allows it to have more flexibility because we have weaker intermolecular forces. The same property of lipid bilayers allows for creation of lipid nanoparticles. Basically, you can engineer lipid nanoparticles based off of the concentration of the lipid in solution to then carry drugs. And so this can actually enhance uptake of certain drugs because it's easy for endocytosis. Cytosis is more efficient with lipid membranes. And this is again governed by intermolecular forces. So I know there's a lot of information. We're just going over a brief introduction of kind of how the chemistry of lipids affects their function. We have our complex lipids, and we discussed our simple lipids, the structure, their properties, and a couple chemical reactions that allow us to go from saturated to um, unsaturated fats and oils. So that'll be our discussion for lipids and membranes. And lastly, we're going to talk about nucleic acids.